Today is April 27, 2015, and this is the very last class, the makeup class for MATB110, Section 1, Calculus 1. So let's get started. So the other thing I have to say is I need to thank all of you who have done an excellent job before the end of last Saturday. I've been watching all the info of the material through Moodle. You did send back the missing scanned copy of the graded homework, the missing copies of the grade quiz, as well as the journals, and together with the scanned copy of the grade midterm exam. And I think most of you have already done this, all right? So I feel very much assured that all the candidates who defend through when it's time to defend the course portfolio. We still have to defend the course portfolio the second time. Okay, so today, as you can see, we are still at week number 14 material because I set the material to only 14 weeks. But the very important topic that we need to cover today at the conclusions of the calculus 1, it's called numerical integrations. Okay, numerical integrations, and that is lecture number 24. Lecture number 24 of the MIT's OCW Calculus 1 course. By the way, before I let you enjoy the very last lecture from David Jerrison's, haven't you noticed that throughout the semester, this is what you are doing? Actually today, in today's college education, right, you can actually go to site which is offered by MIT, which is also offered by another site called Coursera, which is now being added with another excellent platform also offered by MIT with Harvard called EDX. Now in this semester, if you have not experienced it before, okay, I have given you a time to cultivate a habit to follow the very excellent lecture together with the resources provided by very famous and very solid university around the world. This is what I learned. If I'm going to take a course in a specific physical university, neither University of Macau today, I would definitely register myself on a specific mock course like this to help myself to learn. And in this semester, I'm giving you this habit of following the lectures offered by those universities free of charge. Remember, it's free of charge. And step by step, lead you through with some harmonization with myself, the study of Calculus 1. Now you will study Calculus 2 next semester. I will not be the person helping you with Calculus 2, but here you go. I've opened up the door for you. When you took Calculus 2 next semester, continue with the lectures here, okay? In order to finish Calculus 2, you have 10 more lectures here you can study at home during your summer break. And you can also go to MIT's Calculus 2 to study their Calculus 2. And actually, their Calculus 1 includes almost half of our Calculus 2, okay? So that is a very interesting challenge. And here we go. You have all this lecture. You can always go back, study it, look at it, read it, look at the working example. Besides the lecture, as I had said to you, end of the week activity contains all the working examples. You are highly recommended to go to the working examples and study them, and also very important for your final exam. So, may I just suggest to you, do not miss this chance. Now that I open this door for you, you can always go to the MIT link and extract the materials for your own study. In this semester, I'm tailoring the material in the Moodle environment in such a way that we have 14 weeks, so that in each week we basically study 3 sections. Basically, it's 2 lectures, okay? So it's a very important resource for you to learn on your own, compare the educations provided to you at the University of Macau, and also the education that is provided worldwide by such top-notch universities. So, having said that, I do not need to sell for MIT, But you have to notice that relatively recently, the University of Macau has a good connections with MIT professors. And you can see that we have many more seminars now offered by MIT professors. They really go over the way to Macau, okay? And just 2 or 3 weeks ago, we have 2 to 4 MIT professors in the areas of computer science, humanities, and physics now for our lecture. So it's very wonderful. So, having said that, without much ado, let me offer you the very last class for this calculus 1 for MATB110, section 1. Okay? Numerical integrations.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today, I want to get started by correcting a mistake that I made last time. And this was a mistake in terminology. I said that what we were computing when we computed in this candy bar example was energy and not heat, but it's both. They're the same thing. And in fact, energy, heat, and work are all the same thing in physics. I was foolishly considering much more, what am I trying to say? The intuitive feeling of heat is just being the same as temperature. But in physics, usually heat is measured in calories, and energy can be in lots of things, maybe kilowatt hours or ergs. These are various heat units. And work would be in things like foot pounds, that is lifting some weight, some distance, and the amount of force you have to apply. And these are all have conversions between them. They're all the same quantity in different units. Okay, so these are the same quantity, different units. All right, so that's about as much physics as we'll do for today. And sorry about that. Now, the example that I was starting to discuss last time, and I'm going to carry out today, was this dartboard example. We have a dartboard, which is some kind of target, and we have a person. Your little brother is standing over there, and somebody's throwing darts. And the question is, how likely is he to be hit? So, I want to describe to you how we're going to make this problem into a math problem. Yeah. What topic is this that we're going over? We're going over an example, which is a dartboard example. And it has to do with probability. Okay? So, what is the probability that this guy, the little brother, that's it, by a dart. Now, we have to put some assumptions into this problem in order to make it a math problem. And I'm really going to try to make them pretty realistic assumptions, all right? So the first assumption is that that the number of hits is proportional to something like c some constant times e to the minus r squared. All right, so that's actually a kind of a normal distribution. That's the bell curve, but it's a function of the radius. All right, so this is the assumption that I'm going to make in this problem. And a problem in probability is a problem of the ratio of the part to the whole. So the part is where this little guy is standing, and the whole is all the possible places where the dart might hit, which is maybe the whole black border extending beyond, depending on how good a name you think this older child has. So if you like, the part is we'll start simply. I mean, this doesn't sweep all the way around. What we're going to talk about is some section like this, where this is some radius R1, and this other radius is some longer radius R2. And the part that we'll first keep track of is everything around here. It's not very well set. It's two concentric circles. All right? So here I have radius R1, and here I have radius R2. And the region in between is what we're going to try to keep track of. So I claim that we'll be able to guess. This is what I'm calling a punch to start out with. And then we'll take a section of it to get the place where the person is sitting. All right. Now, I want to take a side view of e to the minus r squared, the function that we're talking about. Again, that's the bell curve. And it sort of looks like this. All right, this is the top value. This is now the r axis. And this is up, or at least, so you should think of this in terms of the fact that the horizontal here is the plane of the dartboard, and the vertical is measuring how likely it is that there will be darts piling up here. So if they were balls tumbling down or something else falling on, many of them would pile up here, many fewer of them would be piling up farther away. And the chunk that we're keeping track of is the chunk between R1 and R2. That's the corresponding region here. And in order to calculate this part, we have to calculate this volume of revolution sweeping around. It's really disguised as the ring. This is the side view. It's really the ring because we've been rotating around this axis. All right? So we're trying to figure out what the total volume of that ring is, and that's going to be our weighting, our likelihood for whether the hits occur in this section or this ring versus the rest. To set this up, I remind you we're going to use the method of shells. That's really the only one that's going to work here. And we want to integrate between R1 and R2. The range here is that this is like a solid revolution, so the variable r is the same as what we used to call s. It's range between R1 and R2, and we're swinging it around. And the circumference of a little piece, so at a fixed distance r here, the circumference is going to be 2 pi r. 2 pi r is the circumference, and then the height is the height of that green stem there. That's the minus r squared. And then multiplying by the thickness of just 2 r. All right, so the thickness of the green is r. The height of this little green guy is e to the minus r squared. And the circumference is 2 pi times the radius. Question. So the question is, why is what we're interested in non-distant area? And the reason is interpretation of what I meant by this. What I meant by this is we wanted to add up what the likelihood is that this thing will be here versus here. I wanted to be really proportions on the number of hits times like I wanted it to carry. That's really what I mean. The number of hits in a little chunk. So maybe I'll call it chunk A. A little chunk. Is proportional to the chunk. So there's already an area factor and there's a height. So there are all three measures involved. There's the area. Right? So it's a matter of the what I have to what I intend to say. Yeah, exactly. The height is C times that, whatever this C is. In fact, we don't know what the C is, but because we're going to have a part and a whole for the Y, the C will always cancel. So I'm throwing the C out. I don't know what it is, and in the end, it won't matter. Right? That's very important. Number of hits. So what I mean is number of hits is some chunk. That is, suppose you imagine, so the question is what you when I try to understand what the distribution of dartboard hits is, I should imagine my dartboard. And very often there will be a whole bunch of holes in some places and fewer holes else. I'm trying to figure out what the whole distribution of those marks is. And so some places will have more hits on them, and some places will have fewer hits on them. And so what I want to measure is, on average, the number of hits. So this would really be some time. This constant proportionality is ambiguous because it depends on how many times you try. If you throw 1,000 times, it would be much more densely packed. If you have only 100 times, it would be fewer. Alright? So that's where this conflict comes. But given that you have a certain number of times to try, say 1,000 times, there will be a whole bunch more final in the middle, and fewer and fewer can get thrown away, assuming that the person's aim is reasonable. Alright? So that's what we're saying. So we're thinking that in terms of the person's always leaning to the center, so it's most likely that the person will be the center. On the other hand, it's a fallible person, so the person is. So it's less and less likely to go over. We're just counting how many times this gets to a line time in proportion to the area. Yeah, and R1 and R2 are arbitrary. We're going to make this calculation in general. We're going to calculate what the likelihood is in any possible game. And I want to leave those as just letters. R1 and R2. Because I want to be able to try various different possibilities. Say it again, why do we have to take volume? So this is what we were addressing before. It's a volume because it's number of hits per unit area. So there's a height, there's a number of hits. And then there's an area, and the product of those is, so this is like a histogram of the number of hits. And this should be measured per area, not per length, R. Because on the real diagram, it's going all the way around. There's a lot more area to this red band than just the distance it causes. Okay. So, having discussed the setup, this is a pretty standard setup. I'm on. Yeah, so the question is, why is this realistic? Why is this choice of function where the V2 rockets from Germany hit London. They used this model. It turned out to be the one which was most accurate. So that gives you an idea that this is actually real. The question, this makes it look like people are masters. That is, that they'll all get in the center more often than elsewhere. But that's actually somewhat deceptive. There's a difference between the mode that is the most likely spot and what happens on average. So in other words, the single most likely spot is the center. But there's rather little area in here. In fact, what we're looking at is some little tiny bit in here. In fact, you're much more likely to be out here. So if you take the total of the volume, you'll see that much of the volume is contributed to the active person gets rather rarely. This is not ridiculous. If you think of it in terms of someone aiming at the center, that there's some random thing which is throwing the person off, then there's likely to be the left to the right, or they might get lucky and all those errors cancel themselves and they have to get pretty much near the center. All right? Yeah, another question. How does the little brother come into play? The little brother is going to come into play as follows. I'll tell you in advance. So the thing is, the little brother was not so stupid as to stand on the target. I know. He stood about twice the radius of the target away. And so we're going to approximate the location by some second here, which is just going to be some chunk of one of these things. We'll just break off a piece of it. And that's how we're going to capture. So the point is the target is here, but there is the possibility that the 7-year-old who's throwing towards actually misses the target. That actually happens a lot. So does that answer your question? Okay. All right. Are we ready now to do one more question? Yeah, I'm giving you this property here. I'm telling you that this is what's called a mathematical model, and you can give somebody something like this. In fact, that requires further justification. It's an interesting issue. People, yeah. I'm giving it to you for now, and it's something which really has to be justified in certain circumstances. It is justified. Okay? All right. So anyway, here's our part. All right. This is going to be our chunk for now. We're going to estimate the importance, the relative importance. And now, this is something whose antiderivative we can just do by substitution or by guessing. It's just minus pi e to the minus r squared. If you differentiate that, you get a minus 2r, which cancels the minus sign here. So you get 2 pi r minus r squared. So that's the antiderivative. And we're evaluating it at r1 and r2. So with the minus sign, that's going to get reversed. The answer is going to be pi times e to the minus r1 squared. That's the bottom one. Minus e to the minus r2 squared. That's the top. So this is what our part gives us. And more technically, if you wanted to multiply 2 by c, it would be c times this. I'll say that in just a second. Okay, now I want to work, so if you like, the part is equal to maybe I'll call it c pi as to the minus r1 squared. That's what it really is. So now there's no prejudice of how many attempts you would make. It's 1,000 attempts, a million attempts at the target. Now, the most important second feature here of these kinds of modeling problems is there is always some kind of idealization. And the next thing that I want to discuss with you is the interpretation what's the family of all possibilities. And in this case, what I'm going to claim is that the reasonable way to think of the whole is that R can range all the way from 0 to infinity. Now, you may not like this, but these are maybe my first and third favorite number, my second favorite one. So infinity is a really useful concept. Of course, it's nonsense in the context of the darts, because if you think of the basement wall where, the kid might miss the target and probably hit the wall. He's probably not going to hit on the wall, right? He's not going to get over the edge. So there's something artificial about sending the possibility hits all the way out to infinity. On the other hand, the shape of this curve is such that the real tail end speed is this exponential decrease for time, and that's negligible. And the point is that actually the value go all the way out to infinity is the easiest value to calculate. So by doing this, I'm idealizing the problem, but I'm actually making the numbers come out much more clean. And this is just always done in mathematics. That's what we did when we went from differences to differentials to differentiation and infinitesimals. So we like that because it makes things easy, not because it makes things hard. All right, so we're just going to pretend the whole is from 0 to infinity. And now let's just see what it is. It's c pi times the starting place is e to the minus 0 squared. That's R1, right? It's the role that R1 plays is this, and R2 is minus e to the minus infinity squared, which is that negligibly small numbers. Right, so this is just c pi, because this number is 1, and this other number is just 1 minus c. Now, I can tell you from these two numbers what the probability is. The probability that we landed on the target in the radius between R1 and R2, that's this annual speed, is the ratio of the part to the whole, which in this case just cancels the c pi. So it's e to the minus R1 squared minus e to the minus R2 squared. There's one probability. So the c canceled and pi canceled. It's all gone. Now, again, let me just emphasize the way this formula is supposed to work. The probability, the total probability of every possibility is supposed to be set up to be 1. This is some fraction of 1. We like this percent. Yes. This one is giving so the question is, doesn't this just give the probability? This gives the probability of the ring. But this is a very, very wide ring. This is a ring starting with 0, nothing on this side, and then going all the way out. So that's everything. This corresponds to everything. This corresponds to okay? All right. So now, let's see. Where do I want to go from here? So in order to make progress here, I still have to give you one more piece of information. This is, again, supposed to be realistic. When I was 3 years old, and my brother's friend Ralph was 7, I watched him throwing darts a lot. And I would say that for Ralph, so for Ralph, at age 7, later on, whatever. Ralph at age 7, the probability that he hit the target was about a half. Right? So he hit the target about half the time, and the other times, there was cement on the ball. Just perhaps wrong. That also meant that the points got a little blunter, so it was a little less dangerous. All right, so now, here's the extra assumption that I want to make. So A is going to be the radius of the target. Now, the other realistic assumption that I want to make is where this little kid would be standing. And now here I want to get very specific and just do computation in one case. So we're going to imagine the target is here, and the kid is standing, say, between, so we'll just do a section. This is between 3 o'clock and 5 o'clock. There's more of him, but it's lower down, maybe negligible. So this section is the part, the chunk that we want to see about. And this is A, and then this distance here is 2A, and then the longest distance here is 3A. The longest distance is 3A. So in other words, what I'm saying is that the probability, you're standing too close, the chance, well, it's your brother is about a sixth, right? Because 2 over 12 is 6. That's what it's 6. A sixth of the probability that we're between A and 3A. Right? That's the number we're looking for. Another question. The 2 over 12 came from the fact that we assumed, so we made a very, very bold assumption. We assumed that this human being is actually standing before it's about down here. Maybe it wasn't that tall. So it's really a little bigger than this. But the part of him that was close to the target covered about this section here, between radius 2A and 3. As you'll see actually from the computation, because the likelihood drops off pretty quickly, whatever of him was standing outside the limit mattered. So we're just worried about the part that's closest to the target. Why is it out of 12? Because I made it at 12. And I made it from 3 o'clock to 5 o'clock, so it's 2 of the 12 hours of o'clock. Right? It's just a way of making the section that's really visible. Right? Okay, so now, here's what we're trying to calculate. And in order to figure this out, I need one more item here. So maybe I'll give it a little bit of room. I have to figure out something about what our information gave us, which is what the probability. Sorry. This probability is a half. So let's remember what this is. This is going to be e to the minus 0 squared minus e to the minus a squared. That's what this probability is. And that's equal to a half. So that means that 1 minus e to the minus a squared is equal to a half, which means that e to the minus a squared is a half. I'm not going to calculate data. This is the part about the information about the units. That's what I'll use. Now I'm going to calculate this. The probability right up there is this. And that's going to be the same as e to the minus 2a defined squared minus e to the minus 3a defined squared. That's what we calculate. And now I want to use some of the arithmetic of exponents. This is e to the minus a squared, quantity to the 4th power. Right? Because it's really 2a squared is 4. The quantity is 4 squared. Bring that exponent out. Minus e to the minus a squared to the 9th power, that's 3 squared. And so this comes out to be a half to the 4th power minus a half to the 9th power, which is approximately 1/16. This is negative. This is This is actually why this tails as you go out to infinity under the matter range. This is a much smaller number. So the probability of the whole band is 1/16. Now I can answer the question up here. This is approximately 6 times 16, which is about 1/100, or about 1%. So if I stood there for 100 attempts, then my chances of getting hit were pretty high. That's the computation. All right. Okay, that's a typical example of a problem in probability. And let me just make one more connection with what we did before. This is connected to weighted averages or integrals over weights. But the weight that's involved in this problem was W of R is equal to, so let's just look at what happened in all those integrals. What happened in all the integrals was we had this factor here, 2 pi r, if I include C, which is really, it was really 2 pi C r e to the minus r squared. This was the weight that we were using, the relative importance of now this is not the same as the e to the minus r squared that we started out with, because this is the one-dimensional histogram, and that has to do with the method of shells that gave us that extra factor of r. And that also connects with the question at the beginning, which had to do with this paradox that looks like these places in the middle are the most likely. But that's the plot of e to the minus r squared. If you actually look at this plot here, you see that as r goes to 0, it's going to 0. This is a different graph. And actually, so this is what's happening really in terms of how likely it is that we get within a certain distance of the center of the target. And again, it's not the area under that curve. It's that volume revolution. Okay. All right, we're going to change subjects now. Okay, one more question. Yes.
So that's the graph for weight.
Yeah, that was the graph. That's supposed to be the graph. That would be fine.
Greater than the center. Can you intuitively wouldn't the weight be greatest at the center? The importance.
Well, so the question is, wouldn't the importance of the center be greatest? It's a question of which variable you use. According to pure radius, it's not. It turns out that there are some bands of radius that are more likely for this. It really has to do with the fact that the center, the core of the target is really tiny. It's a target hit. There's a whole band around the outside that has a lot more area, many ways to do that. It's a much larger area. So there's a competition between these. All right, so we're going to move on. And I want to talk now about a different kind of weighted average. These weighted averages are going to be much simpler. They come up in what's called numerical integration. There are many methods of integrating numerically. And they're important because many integrals don't have formulas. So you have to compute them with a calculator or a machine. But these are so now the first type that we've already done are Riemann sums. They turn out to be incredibly inefficient. They're lousy. The next rule that I'm going to describe is a little improvement. It's called the trapezoidal rule. And this one is much more reasonable Riemann sum. Unfortunately, it's actually also pretty loud. There's another rule which is just a slightly trickier rule, and it's actually amazing that it exists. And it's called Simpson's rule. And this one is actually pretty good. But it's clever. So let's get started with these. And the way I'll get started is by reminding you what the Riemann sum is. This is a good review because you need to know all three of these. And you're going to want to see them all laid out in parallel. Okay? So here's the setup. Okay, so here we go. We have our graph, we have our function. It starts out at A, ends up at B, and it goes on to the one paying attention to this interval. This is the function y is equal to x. And we split it up when we do Riemann sums. So this is one, so Riemann sums. We start out with A, which is what we call x0, and then we go a certain distance. We go all the way over to B, and we subdivide this thing. It's delta x's, which are the step sizes, right? So we have these little steps of size delta x. Corresponding to these x values, we have y values. Y0 is f of x0, that's the point above A. And y1 is f of x1, that's the point above x1. And so forth, all the way up to yn, which is f of x. In order to figure out the area, you really need to know something about the function. You need to be able to evaluate it. So that's what we've done. We've evaluated here at n plus 1 points. We've enumerated 0 through n. And those are the numbers out of which we're going to get all of our approximations to. So somehow we want to average these numbers. So here's our goal. Our goal is to average or add. I'm using average very loosely. I'm going to say add up these numbers to get an approximation. To average or add the logs to get an approximation to the interval. Which we know is the area. So here's what the Riemann sum is. It's the following thing. You take y0 plus y1 plus up to yn minus 1, and you multiply by delta x. That's it. Now this one is the one with left handles. So the left hand. There's also a right one, which is if you start at the right hand ends. And that will go from y1 to y1. This one is the right hand. Right hands. Right, those are the two that we've given you. Now I'm going to describe to you the next two. They have a similar pattern to them. And the one with trapezoids requires a picture. Here's a shape, and here's a bunch of values. And we're trying to estimate the size of these chunks. Now, instead of doing something stupid, which is to draw horizontal lines in rectangles, we're going to do something slightly more clever, which is to draw straight lines and diagonals. Many of them actually coincide pretty closely with what I drew there. Although the curve, they miss a little bit. Right, so this is called the trapezoidal rule, because if you pick one of these shapes, say this is y2 and this is y3, pick one of these shapes, this height here and this height is y3, and this base is delta x. This is the trapezoid. Right? So this being a trapezoid, I can figure out its area. And what do I get? I get the base times the average height. If you think about it, if you work out what happens when you do something with a straight line on top of that, you get this average. All right, so this is the average height of the trapezoid. And now I want to add up. I want to add them all up to get my formula. trapezoid. So what do? I have delta x times the first one, which is y0 plus y1 over 2. That's the first trapezoid. The next one is y1 plus y2 over 2. This keeps on going. And at the end, I have yn minus 2 plus yn minus 1 over 2. And then last of all, I have yn minus 1 plus yn. That's a very long formula here. We're going to simplify it quite a bit in just a second. What's this equal to? Well, notice that I get y0 over 2 to start out with. And now, y1 got mentioned twice, each time with a factor of 1/2. So we get a whole y1. And the same thing is going to be true of all the middle terms. We're going to get y2 all the way up to yn minus 1. But then, the last one is unmatched. Yn is only half, only counts half. So here is what's known as the trapezoid. Now I'd like to compare it for you to the Riemann sums, which is just the left. Here's the left one, and here's the right one. If you take the average of the left and right, as in half of this plus half of that, there's an overlap. The y1 through yn things are listed in both. But the y0 only gets counted to half, and the yn only gets counted to half. So what this is a symmetric compromise between the two Riemann sums. This is actually equal to the left Riemann sum plus the right Riemann sum divided by 2. It's the average.
Interesting.
Now this would be great, and it does look like it's close, but actually it's not. It looks if you actually do it in practice, it's not very efficient. Well, it's way better than Riemann. It's still not good. So now I need to describe to you the fancier rule, which is known as Simpson's rule. The idea is again to divide these into chunks. But now it always needs n to be even. In other words, we're going to deal not with just one box. We're going to deal with pairs of boxes. Here's delta x, here's delta x again. And we're going to study the area of this. So let me focus just on that part. Let's reproduce it over here. here's the delta x, here's delta x. Of course, there are various heights. This starts out at 0, this is y 2, this is no second to y 1. All right. Now, the approximating curve that we're going to use is a parabola. So we're going to fit a parabola through these 3 points. And then we're going to use that as the approximating area. Now, it doesn't look like this. It looks like it isn't. But actually, most functions mostly wiggle in one way or the other. They don't switch and run inflection points. So this allows the this scale, but when we get to a smaller scale, this becomes really fantastic. As an approximation. Now, I need to tell you what the arithmetic is. In order to save time, it's on your problem set what the actual formula is. And I'm going to tell you how to think about it. I want you to think about it as follows. So the area under the parabola is going to be a base times some kind of average height. And the base here, you can already see it's 2 delta x. The base is 2 delta x. Now the average height is weird. You have to work out what it is for a parabola depending on those 3 numbers, y0, y1, and y2. And it turns out to be the following formula. It has to be an average, but it's an interesting weighted average. So this is the punchline, if you like, is that there are such things as interesting weighted averages. It's very simple, it just involves 3 numbers, but it's still interesting. It's the following. It turns out to be y0 plus 4y1 plus y2 divided by 6. Y divided by 6, but this is supposed to be an average. Right? Total is 1 plus 4 plus 1. And so it emphasizes the middle more than the sides. And that's what happens throughout. Right? So this is a computation which is on your homework. And now we can put this together for the full Simpson's rule formula. We have here 2 delta x, we divide by 6, and then we have y0 plus 4, y1 plus y2 divided by 6, plus, that's the first chunk. Now the second chunk, maybe I'll just put it in here, starts, this is x2, this is x1, x0, and it goes all the way to x4, so x2, x3, x4. So the next one involves the indices 2, 3, and 4. So this is y2 plus 4, y3 plus y4 divided by 6. Oh no. I think I'll get rid of these 6s. I have too many 6s. All right. Let's get rid of them. Let's take them out of proof now. All right? Thank you. All the way to the end, which is y minus 2 plus 2y minus 1, plus 4y minus 1 plus 1, it's about to divide by 6 and 6. All right. So here are all the chunks. Now, what does this pattern come out to be? This comes out to be the following. This is 1, 4, 1 added to 1, 4, 1 added to 1, 4, 1. You add them up. You get 1, 4, and then it's a repeat, so you get 2, 4, and 2, 4, and 1. The pattern is, it starts out with 1 on the far ends, and then 4's next in, and then it alternates 2s and 4s. Right? So the full pattern, the Simpsons rule, is delta s divided by 3. Now, so see, you cancel these 2 with 6. Getting out of that 2. here I have y0 plus 4y1 plus 2y2 plus 4y3 plus. It keeps on going, keeps on going, keeps on going. In the end, it's 2yn minus 2 plus 4y minus 1 plus yn. So again, 1 and 4 to start, 4 and 1 to end. And then alternating, choosing 4 as the end. This weird weighted average is way better, as I will show you next time.
Well, for the next time, you need to read the lectures number 25 on your own. And I must tell you that in last semester's final exam paper, a lot of questions come from this. But as I said last week, my paper is quite different from last semester's final paper. So you know the answer. All right? So enjoy the semester. Okay? Wonderful thing to have you with me this semester. And I'm going to see you again on May 15 during the final exam day. And then I will read your final exam paper this time. All right? So hope you enjoy this class. Okay, if you have any other question, you can ask me. And I will give you another message telling you the records and the grade. Hope you do not mind my message. All right? It's very important for your semester-based assessment. We hope you know how to make the best use of such wonderful lectures. Okay? See you. Anson was back. I'll check his attendance. All right? Thank you. Hello, I missed your spring concert. Next time you're gonna attend at SPC. You sing, right?
Yeah.
I miss it this time.
What's the section of the exam? I see
Two
the
sections. Okay. Actually, I'll explain once. Two sections. The some question sections. You have to finish and some questions. And each of these is just like a quiz question. It takes you not more than 7 minutes. Okay? And then in the second section is called a long question. I give you 10, you select 5 to do. Okay? 5 from 10. And then they're very comprehensive. That means cover mainly from chapter 3, 4, and 5. Okay? And for those long questions, you will spend about 10 to 15 minutes each. Now remember, the final exam is not open book. You have to know the basics. Okay? But you can do it. You're very good. Yes. So that's it for this makeup class, MATB110, section 1, calculus 1. I personally enjoy this class very much, and hopefully we'll see such a class again next semester. Okay?